We're going to do now is we're going to start looking at some more complicated access patterns and see how that affects our cache behavior. So remember we talked about spatial and temporal locality, which described how we access data. Right? Spatial locality says that we access data that's close together. Temporal locality says that there's a bunch of data that we access at roughly the same time. So far, all the workloads that we've looked at really, the spatial locality and the temporal locality match. That is, we've been iterating over an array, and what we see is that we often get really good cache behavior. So what we're going to do now is start changing that assumption and see what happens to our cache behavior. In order to do that, we'll go through a few steps to build up some intuition, and then we'll dive into this into more detail in class. So let's start with an array that fits in the L1 cache. It's a teeny tiny array, but what we're going to do is we're going to access it like over and over and over again, many, many, many times, lots of times, thousands, hundreds of thousands, millions of times. My question is, if we do that, and we read every byte one at a time, what's the latency of each access going to be? I'm going to claim that it's going to be roughly whatever the latency of the L1 cache is. And you might say, but wait, we know that there will be misses. And you're right. On the first iteration through this array, every new cache line, you're going to take a miss, but then you're going to get hits on all the rest of the bytes in that cache line. So imagine that we have a 64-byte cache line. You'll take one miss, and then all of a sudden you're going to get 63 hits on those next bytes. You take another miss, you get 63 hits, right? So your miss rate is really, really low here, right? It's a little over 1.5%, and your hit rate is like above 98%. And what's more, because this array fits in the L1 cache, on the next iteration, you'll take no misses. And after that, no misses. So you're going to take no misses on most of these iterations and not even that many misses on the first. So the performance is going to approximate that of the L1 cache. But now I want you to consider a different workload. We still have a teeny tiny array, but what we're going to do is we're going to access every 8th byte. So you're going to think for a minute and say, well, that means I'm going to take a miss, and then I'm not going to read 63 bytes. I'm actually only going to read about 8 more bytes in a cache line. So now my miss rate is much higher. It's like 1 out of 8. But we're still in the case where the array fits in the cache. And so in all the subsequent iterations, all those data are still in the cache. I'm going to get hits. So even in this case, we're still going to approximate the latency of the L1 cache. Okay. Now this kind of access, though, where we touch periodic bytes is called strided. Okay, it doesn't mean we touch random bytes. It means there's some interval between the bytes that we touch, and that is called a stride. And strided accesses are actually really handy when we want to analyze cache behavior. Let me show you why. We're going to move away from our teeny tiny array, and now we have a really big array. Okay, so it's way bigger than the cache. So now, if you access every byte, what will your latency be? Well, let's see, it's bigger. So now how do we think about this, right? My array is bigger than the cache, but I'm still accessing every single byte. So I'm still going to get a lot of hits. And in fact, the larger your cache line, the better your hit rate, right? So we already saw that 64-byte cache line, we were going to get a hit rate of about 98%. And if you start doing some math, what you see is that as your cache lines get bigger, even though this data exceeds the size of the L1, your average access time ends up being pretty close to that of the L1. So let's imagine a scenario where your misses are 5 times slower than your hits, which is not an unreasonable assumption for 2 adjacent levels in the memory hierarchy until you get to disk, right? L1 relative to L2, L2 relative to L3. So if we have a 32-byte cache line, then my miss is going to cost me 5 units, whatever a unit is. But then I'm going to get 31 hits that are 1 unit. And so I end up, my average access time ends up being 1.13, right? So it's like 13% slower than if I were just getting the pure L1 performance. When I go up to a 64-byte cache line, we're only getting about a 6% hit. And by the time I get to a 128-byte cache line, it's only a 3% hit. So the bigger the cache line, if I'm really reading just every single byte as an individual access, I get pretty close to the cache size, okay? So the sort of how far away you are from the pure cache performance is going to be a function of how big that cache line is. All right. So next, now let's say that the L1 is 4 kilobytes. And instead of accessing every 1 byte or every 8th byte, I'm going to access 1 byte out of every 4 kilobytes. Now what's my average latency going to be? Well, let's see. So I'm going to take a miss on the first byte, and then I'm going to skip ahead 4 kilobytes, and I'm going to get another one. And oh, by the way, let us assume a direct mapped cache. And so now all of a sudden, every single one of these, if I really am getting every 4K bytes and my cache is exactly 4K, I am always going to miss, because that byte is going to map to exactly the same location in the cache every single time. So now, instead of getting the latency of the L1 cache, I'm really going to get the latency of either the data source or the cache below me. Okay, so one of the ways that we can figure out how large caches are is by sort of changing these stride patterns and seeing what happens to the performance, right? And it turns out that strided patterns are actually pretty common. So if you have a whole bunch of arrays, structures, and you pack them into an array, but you're only accessing one field in those structures, that actually will generate a strided access pattern. A lot of matrix operations will generate strided access patterns. And many sort of large-scale computational scientific experiments or scientific applications will exhibit these strided patterns. So it's a really common pattern, both for applications, so it's important to understand, but also it's a great tool to use to try to measure performance of a system and figure out what its memory system looks like. And so what I want to do is just wrap up with a little bit of an example about what I mean by using these strided patterns to figure out what your cache hierarchy is. So consider this graph where we have the size of some array on the x-axis, and then on the y-axis, we're going to say, how long does it take us to do something? So let's consider the workload where we read every byte of the array many times. This is the workload we've been looking at. So we already said that when your array is roughly the size of the L1, we get L1 performance. And in fact, even as that array gets bigger, we continue to get L1 performance. But now let's change the workload, and now we're going to read every nth byte. And let's start by sizing n to be exactly the size of a cache line. So we're going to make sure that on every access, we're going to access a new cache line, but we're going to read the array many, many, many times. So when the array is exactly the size of the L1, we're in good shape. The performance is still that of the L1. But as soon as our array is a little bit bigger than that, remember, we're going to take a miss on every single access because we're doing cache line size accesses. Then what's going to happen is I'm going to start getting the L2 cache performance because I'm going to fall out of the L2. Now, at some point, if my array gets big enough, it might be bigger than the L2. And so now I'm going to start potentially falling out of the L2, and what I'm going to see is latency that looks more like the L3. And so what you see are you get these patterns, and you, depending on the architecture, you can actually see pretty clear step functions as your data, oops, it fell out of that cache and now it's going into the next one. So you can look for these big jumps to figure out how big your caches are. And we'll practice doing this, both looking at workloads and estimating their cache behavior, but also looking at some performance characteristics and seeing what happens. Okay, and just like we saw at the L2, you can see when you fall out of the L2, you can start to see the same behavior. And what happens when you fall out of the L3? Sure enough, you start to get performance that looks more like main memory. So this is just to give you an overview, start to get some intuition for how your system behaves as a function of how you access memory. And so what I want you to think about before coming to class is what would this look like if the stride were half the size of a cache line? What if it were twice the size of a cache line? And I'm not looking for like detailed performance numbers. I'm looking for some intuition and sort of a vague idea of like, oh, I guess it would, behave slightly differently. Okay. And now what happens if I access bigger units of memory instead of like each individual byte? So not an exercise, but a thought process to think about so that when you come into class, we'll be all ready to talk about this. And I look forward to seeing you.